Good day, everyone, and thank you for attending this session. In the next 15 minutes, I will describe a transformative architecture that leverages point to multi-point coherent optics, or XR optics. But first, let's take a look at the current mode of operation. Okay, so since the inception of optical networks, there has been a significant misalignment between the actual network traffic patterns and the technology used to transport this traffic. Network traffic patterns, particularly in metro networks, are overwhelming hub and spoke, with numerous endpoints consuming traffic that is aggregated by a small number of hub locations. In contrast, the optical connectivity solutions have been implemented using a strictly point-to-point technology, where each end of the connection is required to operate at the same speed. So you have a 10 gig on one end, you have a 10 gig on the other end, 100 gig on the other end. And the result is an extremely inefficient transport architecture that requires a large number of bookended transceivers, as well as a numerous intermediate aggregation devices to upspeed the traffic flows. And this problem has been, if you look at the other industries, the problem has been solved in the mobile industry, for example, where a single radio tower can talk to many radios embedded in our cell phones. However, this problem still remains in optical networks, where each laser has to be bookended, operating at the same speed, at the same rate, requiring twice the number of transceivers. So if you have 16 endpoints, you need 32 transceivers operating in a point-to-point fashion. This is too expensive and too operationally challenging, as well as it's inefficient. So this is actually a snapshot of almost, if not all, aggregation networks now. You have many endpoints generating traffic. Those endpoints are connected using a point-to-point optics to an aggregation site, as you can see on this slide, where switches and routers pack the traffic into higher bitrate wavelength and then transport to the hub sites. Again, the number of transceivers needed is twice the number of endpoints, in addition to the electrical aggregation sites. And this problem actually can be solved with XR optics. So XR optics is the industry's first scalable point-to-multipoint direct low-speed to high-speed coherent pluggables, or the industry's first point-to-multipoint laser. And XR optics allows a single 400 gig to connect simultaneously to 16 endpoints, providing bandwidth in 25 gig increments. And as a result, reducing the number of transceivers by over 50%, going from 2 times n, where n is the number of endpoints, to n plus 1. The example I mentioned earlier, 16 endpoints requires 32 lasers, while with XR optics, it requires 17. And going from chassis and transponders to pluggables, a 100 gig XR pluggable at each endpoint and a single 400 gig XR pluggable at the aggregation side. This alone reduces the number of transceivers by 50%. In addition, there's a massive reduction in power and footprint, as these pluggables are way too compact and less power hungry than typical and conventional transponder-based solutions. Another point to mention here is that XR optics uses 16 QAM modulation, so it provides a very good optical performance than gray optics. So we can push this aggregation point deeper into the network, all the way to the hub site, replacing boxes and boxes at the aggregation site with a simple passive splitter combiner device. And this has a major positive impact on OpEx, as well as significant simplification of the network. There is also another advantage of XR optics is its flexible end-to-end management. So XR optics supports embedded communication channels to provide a complete and thorough management system between all XR optics modules, hub and spokes, the hub as well as the endpoints. And this management system facilitates the bandwidth allocation and the connectivity matrix between the different destinations, between the leaves and the hub, as well as managing alarms and network status, allowing XR optics module to act as a subnetwork with within a much larger configuration. And this is absolutely key. So how does it work? How does XR optic work? So XR optics utilizes a digital signal processing, or DSP, to subdivide the transmission and the reception of a given wavelength spectrum into a series of small frequency channels called digital subcarriers, or Nyquist subcarriers. And these digital subcarriers can be independently managed and assigned to different destinations, enabling the industry's first scalable point-to-multi-point direct low speed to high speed optical transceiver connectivity. As you can see on this slide, a single 400 gig optics, the hub, generates 16 25 gig digital subcarriers. One or multiple digital subcarriers can be combined and assigned to a specific destination to provide the required bandwidth. And XR optics transceivers are designed to be equipped into a wide range of networking equipment, including Ethernet switches, routers, wireless baseband processing units, cable MSO aggregation platforms, packet switch ports, PON head-end aggregation systems, data center servers and switches, and so on. So they're not limited to optical, but they can be equipped in a wide range of networking equipment. And XR optics also meets the most common standards for other coherent pluggable optics like 400 gig ZR, including the physical form factor, the QSFP28, the CFP2, the QSFP56DD, or OSFP for 800 gig, and network management, as well as network management interfaces. So another key aspect of XR optics is XR optics can be deployed on a fiber pair and a single fiber, or a single fiber working, if you want. And this is actually, this slide here is a visual representation of how XR optics work over a fiber pair. So the hub on the right-hand side has a 400 gig XR optics that sends 16 subcarriers to each leaf or endpoint. And through the management system, the leaf can lock on what is entitled to. For example, subcarriers 5 and 6 in this example, which is 2 times 25 gig. That's equal 50 gig bandwidth or capacity. And once locked, the leaf can start transmit back over the subcarrier 5 and 6 back to the hub. And data protection is ensured through encryption. Now, if we want to increase the capacity of that leaf, we simply just send additional subcarriers. Let's say we send subcarriers 7 and 8. So now the capacity is doubled. It's going from 2 subcarriers to 4 subcarriers, or from 50 gig to 100 gig. And that's done purely through software without any truck rolls. And that can be done as well through automation. Another example here, XR optics work over existing single fiber working, or SFW, because you have a lot of cell towers that are connected over a single fiber, PON infrastructure, for example. So this is how it works. So in this example, we can see that the hub, the subcarrier number 5 is being sent downstream. The hub does not transmit subcarrier number 6 because it will be used as the upstream traffic coming back from that leaf over a single fiber working. Now, if we want to increase the number of subcarriers in any direction, and in this case, we're sending 2 additional subcarriers downstream for a total of 3, and we have 1 subcarrier being transmitted upstream. This is an example of asymmetrical traffic pattern. So I have 75 gig going downstream, and I have 25 gig coming up upstream. And XR optics is so flexible that it can work in symmetrical and asymmetrical traffic patterns. So if we go back to the problem statement about aggregation networks being too costly and complex, XR optics provide many advantages. First, on the left-hand side, an embedded communication system that facilitates the bandwidth allocation and the connectivity matrix between the different destinations, as well as managing the alarms and the network status. So XR optics modules can be managed as part of the optical network. This is absolutely key. The second is XR optics is intergenerational. It's intergenerational interworking aspect. This unique capability or ability for a low-speed transceiver to communicate directly and simultaneously with high-speed transceivers at the hub eliminates the situation where a single site upgrade triggers the need for a network-wide upgrade. It's widely known, it's no secret that it's widely known that network-wide upgrades, when you have to upgrade all the nodes and all the links, require a significant capital investment, labor intense, and often result in inefficient utilization of the bandwidth, where you have low bandwidth consumption sites are provided with a capacity significantly more than the actual demand. So now, for the first time in the industry, XR optics decouples network upgrades from node upgrades, enabling certain spans and links or nodes, hubs or spokes to be upgraded to higher capacity while the rest of the network remains unimpacted. And that's actually allows to align the capex with actual capacity demand. Uh, Third is the dynamic capacity allocation without complex planning and time-consuming truck rolls. So capacity can be allocated easily across the network permanently or over a certain period of time. And this allocation can be done manually or can be triggered by software automation. XR optics also enable a flexible deployment model, as I've seen in the previous examples. They can be deployed over a fiber pair or single fiber working, fixed grid or flex grid, cascaded ROADMs or FODEM architectures. Um, and XR optics, finally, is XR optics is more than just a set of pluggables. It's a system in a pluggable form factor. XR Optics has several card and system level features, such as in and out band communication channels, topology awareness, allowing automated turn up and remote management of those XR Optics plugs deployed at remote locations directly from the hub without truck rolls. Ensuring a clear demarcation points, which is absolutely key. You want to reinforce the SLAs, as well as XR Optics supports a layer one wire speed encryption, point to multi-point aggregation for layer one and layer two traffic, topology awareness, control plane features, constellation power management, OSAs, optical spectrum analyzer is already embedded into the optics, and much more features. So it's the system level features that being contained or being shrunk into a pluggable form factor. So I'd like to finish with a slide showing the order of magnitude of the savings enabled by XR optics. In this ECOC conference later today, there's a session where Infinera and Bridge Telecom described the outcome of a case study comparing XR optics to conventional solutions, and the benefits were in the excess of 70% in terms of TCO reduction over a 5-year period. And we've been, these results were very consistent with other case studies we've been performing with other tier one service providers, as you can see on this slide. This particular slide is about a North American tier one service provider where the TCO reduction are in the order of 76% enabled by XR optics compared to conventional solutions. Let me just finish with an overview of the applications. So XR optics can be deployed in a point-to-point and a point-to-multi-point applications. However, they're optimized for a point-to-multi-point or hub and spoke traffic patterns. This includes cable fiber deep applications, DAA, 5G wireless backhaul applications, traffic aggregation in metro areas, as well as DSL or PON backhaul. So for more information about XR optics, please visit infinera.com, and thank you for attending this session, and have a great day.